So my talk kind of fits into one of the broader themes of the workshop that's been explored in some of the earlier talks by Pau Figueras and by Franz Pretorius. So it's really this idea of, if we had some new physics, what could that new physics look like? And so, like in those talks, it's not so much that the models that I'm going to talk about are sort of really something we think definitely exists. It's more that they're kind of toy models to try and probe what new physics might actually look like in strong gravity environments. So you should sort of take it in that vein. So in terms of the plan for the talk, the overall message of the talk is that although black holes, stationary black holes, have no hair, there are loopholes which permit you to have dynamical hair that may not be stable indefinitely, but can be stable long enough for it to be of kind of astrophysical interest. And in those cases, we would quite like to know what are the gravitational signatures of that dynamical hair. How does that manifest? So I'll start by giving some background on the kind of models that I'm talking about and how we simulate them. And then I'll talk about the role of numerical simulations. So when I say numerical simulations, I'm primarily talking about time domain evolutions of this kind of dynamical hair, where we start out with some initial conditions and we evolve them forward in time, and we ask the question, what happens? What happens next? So these kind of simulations can contribute in two key ways, I think. Firstly, we can just ask questions about the robustness of dynamical hair. So really, this is an important question before we go on to the second one, which is what these gravitational signatures are. Do we really expect this dynamical hair to stick around long enough to actually be of interest in astrophysical cases? Or is it very sensitive to the environment or to self-interactions or to things like this? So in a way, we should answer the first question before we start trying to answer the second question. That's not quite how it works. We tend to work on both at the same time. I think that's fine because we learn, these are just toy models after all. And so we learn things from doing both, from attacking both problems. But in this talk, I'll mainly focus on the first question. And then if I have time at the end, I'll just mention some of the interesting points on the second question. So as I said, I'm mainly talking about time domain simulations, but I won't necessarily be talking about full numerical relativity. So particularly in the first question, a lot of the simulations can be simulations on a black hole background, for example, where the background is fixed, and we just evolve the fields on top of that background. And that can be advantageous because it can help us to follow longer timescales. And if I have time, I'll close by mentioning what I think are the key outstanding challenges. Okay, so I should probably have Matt Choktrick's warning about the lack of rigor in the next few slides. But broadly, we know that stationary black holes have no hair. But of course, when we observe astrophysical black holes, they have, for example, an accretion disk. And the way we reconcile these two facts is to say, well, okay, no stationary solutions to black hole plus matter exist. So over time, all matter is either going to fall into the black hole or it's going to be radiated away. And then it's going to leave us with a bare black hole that's fully characterized by its mass and its spin and its charge. And there will be no details left of the original matter, so we won't know what matter went into it. So for the time when the matter is around it, of course, it's not a bare black hole. But of course, the end state will be a bare black hole. So another kind of corollary, I guess, of this is usually in the theories that I'm going to talk about, which are all minimally coupled scalar and vector fields, you can't source the fields using curvature. So no matter how much I churn up my space-time by binary black holes, if I start with zero scalar field, for example, in the space-time, at the end I will still have zero scalar field. So the curvature does not act as a source. So that's not the case in modified gravity theories, or at least some modified gravity theories, where the curvature can actually act as a source of the hair. So I won't be talking about those. So I will be focusing purely on GR plus minimally coupled fields, so to absolutely the simplest case. But some of what I say, could be relevant in these cases where, as I say, the scalar represents an additional degree of freedom in a modified gravity theory. But I won't touch on that. But just to highlight that that's a motivation for some people to consider these modified gravity models, that they actually have a way of sourcing the additional scalar field from the curvature. So what about loopholes? The assumptions behind the no-hair theorem are that the matter fields inherit the symmetries of the metric. So if the metric is stationary, then so are the matter fields. So one of the key ways that we get around the no-hair theorems is to have a field that's perhaps oscillating. So although it is kind of stationary in the sense that the oscillations are periodic and they don't grow in time, the matter is has a time dependence, whereas the metric doesn't. The other loopholes are basically related to being in an asymptotically flat space-time, the hair being regular at the horizon, and as I mentioned, modified gravities can get around this. So one of the key interesting examples that makes use of this loophole is the example of superradiance. So in superradiance, what you have is that you have, so actually this is a movie, so maybe let me play the movie and then you've got something to look at while I talk. So you have a scalar field, a seed of a scalar field, and it scatters off a spinning black hole. And as it scatters off, it's amplified, it extracts some of the rotational energy of the black hole. And then because it has a mass, it's actually trapped in the vicinity of the black hole in a potential well. And so this can repeat, this process can repeat this scattering, and gradually this will build up a scalar cloud around the black hole. So you can construct cases of this which are properly stable, in the sense that the amount of energy that's being extracted from the black hole is exactly the same rate as is falling into the black hole and kind of replenishing the spin of the black hole. So you can set up quite finely tuned cases that in principle will be stable long term. But in general, when people talk about superradiance, they have in mind that it's a process that will happen with a finite duration. So you will have this initial seed for the superradiance can come from quantum fluctuations around the black hole. So that kind of goes against what I said previously, where curvature can't source the scalar field. That's a classical statement. If you have quantum fluctuations, then you can create this seed, which will then go on to be amplified by the superradiant process. So the idea is that this cloud will build up at some point. The black hole will actually spin down and lose its angular momentum, such that this process saturates. And when that happens, you're left with this cloud, which will gradually decay via great gravitational radiation. So at some point, again, you're going to end up with a bare black hole. So it's not going to give you a real hair, in a sense, in most sort of general situations. But this is a process which can have an astrophysical timescale. So a second interesting case, which I think is less talked about than superradiance, is this case that was proposed by Ted Jacobson, where if your asymptotic value of the scalar field is varying slowly over time, you do actually gain this 1/r dependence in a scalar field, for example. So you do actually generate this kind of non-trivial hair around the black hole. So you can see that this obviously breaks the first assumption. It also breaks the second assumption because, of course, if you have an asymptotically time-varying field, that tells you that you have some energy density asymptotically. And so you're not in vacuum flat space. You're in some kind of cosmological space-time. But after all, we do live in cosmological space-time. So that was ultimately the motivation for this suggestion. You can ask the question, well, what if it's not varying slowly, as it was in this case? So as time goes down, this is what happens. What if I actually make the asymptotic value of the field oscillate? So this is what happens. So you can actually see that really this Jacobson hair, what it really is actually a time delay around the black hole. So the scalar field is oscillating more slowly at the black hole position. It's just the usual gravitational time dilation effects, and so you get this kind of delay. So you can then do this for a bit longer, and you start to build up more of this interesting configuration. And finally, if you do it for long enough, you get this profile. So this is actually the confluent point functions, which are solutions to the Tucholsky equation. So that's what a mathematician would say. So what a physicist would say is that this is actually accretion of the scalar field onto the black hole. So I think you can see that. I don't know if I can play the movie again. Yes, I can. So this is asymptotically, you have some reservoir of a scalar field that has some energy density, and that is flowing into the black hole, and the energy density around the black hole is enhanced, essentially because of this Jacobson time delay effect. So as I say, that's not mentioned so much, but this is actually quite motivated, particularly in the case where you have your scalar field being a dark matter candidate. Then you do have this idea of a reservoir of scalar field. That's your reservoir of dark matter around the black hole. Okay, so simulating dynamical hair in strong gravity. So how do the simulations work? So it's very straightforward. So we are evolving just the Klein-Gordon equation in the spin zero case. So the spin, obviously, Klein-Gordon equation is a wave equation. So this gives you this wave-like behavior that you can see very clearly in this picture of accretion. And you actually have pressure support on length scales of order set by the mass of the scalar field. So this is what can actually give you some support against the field kind of collapsing into the black hole. Actually, where the mass is very small, you can get very, very long-lived clouds around the black hole because it gives you this, as I say, this kind of pressure support. So I think it's kind of easy to read off from the simulations of scalar field the kind of physical properties of the fluid. So, for example, the momentum of the field and the energy density can just be recovered from these quantities. So again, I think it's play the movie again. So I think it's obvious from this, what's happening. Your amplitude is increasing, so this tells you that your energy density is increasing. Your gradients are increasing here, so it's telling you it's moving faster as it comes towards the black hole. So this is, as I say, this is exactly what you'd expect from accretion, but seeing it in the sort of scalar field picture, it just looks kind of slightly different. So there are numerous motivations in particle physics for scalar degrees of freedom, so things like axions, scalars from compactifications and string theories. I mentioned already that it's a candidate for dark matter, particularly fuzzy dark matter. So as I say, this case is quite well motivated, I think. So I said I will also talk about vector fields. For spin one fields, the field obeys the proper equation. So it's essentially electromagnetism, but where the field has a mass. So again, you can work out the underlying properties of the particles, but okay, it's a little less obvious from these expressions and from looking at the configuration of the vector field to try and extract them. But nevertheless, you can easily solve these equations and recover the kind of physical measurable quantities. So I guess motivations, there are models which have dark photons as being some component of the dark matter. There's also been an interesting suggestion that I'll mention more of a bit later about the potential for photons to acquire an effective mass in a plasma, in which case they would obey something like a proper equation. And finally, one of the key motivations from a numerical perspective is that the vector field can be a good toy model for scalar fields. So I think when I say this, potentially you should think, well, that's a very strange thing to say. Why on earth would you use something more complicated to model something that's clearly a lot simpler, the scalar field case? And the reason is that is this first point that I mentioned here, is that vectors actually scatter more efficiently off spinning black holes. So this process of superradiance happens much more quickly on the typical timescale of the black hole, so say the light crossing time of the black hole, compared to the scalar case. And that actually makes the difference between being able to simulate it in a time domain simulation and basically not being able to see anything within the timescale of the simulation. So they're very important for that reason. But obviously there are differences. You have more degrees of freedom. You actually have an additional constraint on the initial data. And physically having a non-zero asymptotic value of a vector field, for example, is a strange thing if you imagine cosmology, because the universe is isotropic, so we don't have a preferred direction. So there are definitely differences, and it's quite interesting to consider to what extent are they interchangeable, and that's something that will be important in the work that I've done on the robustness of these kind of dynamical hair. So I wanted to mention the previous lots of interesting, excellent works on superradiance, and in particular the work of Will East and Franz Pretorius, where they did use a vector field to simulate superradiance and showed that the endpoint of this superradiant instability is a smooth saturation of the instability. So it's a kind of gradual spin down of the black hole and a gradual saturation of the mass of the cloud. And that wasn't necessarily obvious beforehand. It wasn't necessarily obvious that there wouldn't be some big bang and some throwing off of the scalar field or some very rapid spin down. But actually, it's a very adiabatic process, this kind of turn off of superradiance, which justifies then a lot of analytical work where that has been assumed. Another interesting consequence of their work was to work out what kind of mass the cloud can achieve before saturation. And it's actually quite high. You can get sort of around of order 10% of the mass of the black hole in this superradiant cloud at the end of the process. And so that's particularly interesting because it tells you something about the energy density that you can achieve in the cloud. So if you take this figure of 10% of the black hole mass, and then you know also that it's concentrated within roughly 10 Schwarzschild radius of the black hole, this gives you a rough estimate for what the order of magnitude of the energy density is. And that gives you this number 10 to the minus 5 when you're comparing it to the kind of curvature scale of the black hole itself. And this number is the one that's really important when you consider any kind of gravitational effects of the cloud. So this is going to tell you about impacts on ring down, inspiral merger, things like this. So really how much it's going to change the dynamical properties around this black hole. So you would really like this number to be, order 1. 10 to the minus 5 is small, but it's not actually tiny. So this number, I'll mention at the end, actually gives you some hope that you might be able to observe these clouds with the LISA gravitational wave detector. where you're going to observe something of the order of 10 to the 5 orbits before of a small object spiraling into a supermassive black hole. And so potentially integrating over that high number of orbits will give you an order 1 deviation in, for example, the phase of the gravitational wave signal. So just a very quick comment on the non-relativistic description. So it's quite common to, for these fuzzy dark matter candidates, for example, to make a non-relativistic approximation where you take your scalar field and you split it into a slowly time-varying part and some part that's oscillating more rapidly with the mass, according to the mass of the scalar. So you make this assumption that the time derivative of this part is, as I say, much smaller than the mass. And then you can show that this new field psi obeys the Schrödinger-Poisson equations. So in relativistic simulations, which I'm going to be talking about, so around black holes, these timescales are not different, they're similar. And so we can't separate the fields out in this way, which is the real limitation of these kind of simulations. Essentially, the very long timescales that you need to follow. So you have to really follow every oscillation of this field. You can't kind of average over these oscillations, which allows you to do these very long timescale simulations. You have to really follow those individual oscillations because they are, as I say, on the timescale of interest. Okay, so let me talk about the question I wanted to get to, so robustness of dynamical hair. So this is work that's I've been doing with Thomas Helfer, who's currently a postdoc at Johns Hopkins University. So specifically, we've been interested in the question of interactions within environment. So there was this paper that suggested, as I've mentioned, that photons would acquire a mass in an astrophysical plasma around a black hole. So we might like to, so if this is the case, then they don't have a constant mass throughout the space-time like a fundamental scalar field. They will have an effective mass that varies in space. So a toy model to test this is to have a spatially varying mass function for the scalar degree of freedom, or really in this case, you are interested in vector fields. But the first work that was done on this used scalar fields as a proxy for the vector case. And they did this very nice work where they used a method from Sam Dolan, where you decompose the field into spherical harmonics. And you can consider a sum over your L modes for each value of M, and for each value of M, the modes are independent. So you can work out the time evolution for a scalar field, even though the time scale is very long, provided you make some appropriate ansatz about what the mass function is that allows you to still make the equation separable. So although this assumption restricts you somewhat in the cases that you can study, it's a very efficient method. And ultimately, their conclusion was that astrophysical configurations of the plasma are actually likely to disrupt this superradiance process. So even if you could think that you could start this superradiant process, ultimately these kind of spatial variations in the plasma, which will change the spatial variation of the effective mass, will basically cause superradiance to stop working. So we wanted to compare this to the vector case. So I mean, ultimately, this was motivated by thinking about vectors. And as I said, in some ways, they're very interchangeable. It's not always entirely clear whether one is a good proxy for the other. So we've been essentially looking at the same cases, performing the simulations with a vector field where we have this spatially dependent mass. So ultimately, our conclusions are that so far the behavior for the vector field is very consistent with that of the scalar field. And so I don't have anything sort of shocking to tell you in terms of what happens, but I can show you a few nice examples. So we can go to more general configurations of the mass, which is kind of interesting. We can try some with an angular dependence around the black hole, sort of relative to the spin axis. But I think ultimately we support their conclusion, which is that spatial dependence that are kind of physically motivated do tend to spoil the process of superradiance. So for example, if we take this profile for the mass, so this is motivated by Bondi accretion. So if you have Bondi accretion onto the black hole, you'll tend to have a density that grows as you get towards the black hole, and that will give you an effective mass for the photon, which grows as you get towards the black hole. And so I'll show you what happens when you put a seed of scalar field around the black hole. So very, very quickly, you can see what happens. You just get this burst of the radiation being given off, and it doesn't generate a superradiant cloud at all. Whereas if you add an asymptotic mass plus this Bondi accretion profile, you can actually get a stable superradiant state. So really the key thing is to have this asymptotic value of the mass be consistent with the superradiant mass that's required. Having this sort of spike doesn't necessarily disturb it, but certainly the fact that it goes to zero far away will prevent superradiance from happening. So a second interesting question that we've been considering is regarding self-interactions in the field. So this is a subject with quite a long history, going back to these papers by Yoshino and Kadama back in 2012, where they suggested this very interesting thing that if you had attractive self-interactions in a bosonic cloud, you could actually have a bosonova, which is something that occurs in condensed matter systems as well. So that you'd have the superradiant growth, and at some point you'd reach a critical point where the self-interactions become important. And they say, either you could saturate or you could have a bosonova. And the conclusions from their studies was that you would actually end up here, that you would have some kind of explosion. So this was the kind of prevailing wisdom. But actually, just this year, there were these really interesting papers suggesting that this may not be the case. So first, this nice paper by Masho Variakta and collaborators, where they were looking in the non-relativistic regime at this case. And what they found from their calculations is that actually what you would get is a period of superradiant growth. But once the self-interaction started to be important, you would actually saturate before you reached the stage at which a bosonova would happen. And this saturation relates to transitions from this superradiant state into higher modes. So into higher modes, and also from the cloud falling back into the black hole and also being radiated off to infinity. So these are things that would be triggered by the self-interaction. And they claim that this would saturate the superradiant instability prior to a bosonova happening. So you wouldn't get this kind of explosion. So they of course say that their calculations only apply in the non-relativistic regime. That was the limit of their calculations. But they suggest that from what they can see, it's probably also not going to happen in the more relativistic regime. There was then a follow-up work where this group of EMEA and collaborators said that was kind of a questionable conclusion. So they did a renormalization group analysis of the superradiant growth. And so they said, essentially what they said was, well, it's not clear. So they say that, these are the calculations, these are what you get. But at this dotted line, this is actually where they think that the perturbative calculation breaks down. So they think that you can't really trust these lines beyond this point. At this point, you would need relativistic simulations to resolve what's actually happening. So they don't necessarily say that this is wrong. They just say that they think that the perturbation scheme potentially breaks down by the point that you get to this saturation. So we wanted to test this. Since we want to perform time domain simulations, we decided to do it with the vector field, where we can observe the full build-up prior to either saturation or bosonova. And we picked a quadratic potential, so of this form, where the leading order is then attractive, and picked the fastest growing mode for the vector case. So in the simulations, we can actually neglect back reaction, and then only the combination here determines when the onset of the self-interactions happen. So you actually have a rescaling symmetry between lambda, your coupling, and the amplitude of the field. So we can always find a regime where this is consistent. We can always say, okay, we're at an earlier part of the buildup where the amplitude is smaller and we still haven't extracted all of the rotational energy from the black hole. But in that case, we need to make the coupling much larger. And of course, in some regimes, that might be unphysical to have such a large coupling. But in principle, you can always find a regime where that's true. And so that means from a computational perspective that you really only need to do one simulation of this. So once you've fixed, you choose a value for lambda, you then grow the value of your field. And at some point, you're going to hit the amplitude where something happens, where you start to see the nonlinear effect, or rather the self-interaction effect. So this is what we did. So we evolved it. So this is just to give you a kind of sense of these simulations. I think one of the things that really surprised us in these simulations was how much resolution was really required. So I had a really new respect for the simulations that Will East and Franz Pretorius did. It was really, really high resolutions required of the horizon area, particularly to try and achieve the right growth rates in the non-self-interacting rate, to check that we get the right kind of rates, and then to add in the self-interaction and see what happens. So what do we see? So early on, we just see the normal superradiant state. Later on, we do start to see evidence of this kind of transition to higher modes, energy being radiated. You can see quite clearly here that there's some radiation going on of the cloud. Also, not so easy to see, but you're actually seeing oscillations in the accretion onto the black hole, so the energy transfer with the black hole itself. So it does seem to be destabilizing exactly in the way that Masha Bariapta and co suggested. However, we find that we ultimately get to the top of the potential without anything significant happening, so without any kind of saturation occurring. And of course, once we get to this point, we can't continue the simulation because ultimately the potential becomes unbounded. So what that means is really that the ultimate endpoint of this will be determined by higher order interactions in the field. So we should have some kind of phi to the sixth, which then brings us back up here. But then it's the phi to the sixth term that's actually going to determine what happens, and not the phi to the 4. So in a sense, what we found was that this was kind of too strong. You can't beat the superradiance. So the superradiance just builds you up. And although you get some instability, as I say, you can get to the top of the potential without any kind of saturation. So it seems likely that in vector fields, at least, you'll be able to reach a kind of Bosonova state. But in a sense, this is not answering the original question that was posed, because that was for scalar fields where the rate of superradiance is much slower. So it's entirely possible that you still do indeed, as I say, we see evidence that these saturation processes are beginning to occur. They're just not fast enough to beat the superradiant buildup. But maybe in the scalar case where the rate is much slower, they are. So I think it's still a slightly open question. But this gives evidence that at least in the vector case, you could have this Bosonova. So I think I don't have that much time left. I just wanted to show you some ideas about gravitational signatures of dynamical hair. So one interesting idea that I already mentioned is that you could have this small object inspiraling into some larger supermassive black hole that's a target for LISA. And it's been suggested that in that case, the impact of the scalar field could be seen on the gravitational wave signal. So one of the things that we've been studying is the effect is the role of dynamical friction in that process. So the fact that as the smaller object moves through this scalar field, it generates a tail, which actually creates a drag force, a gravitational drag force on the object. And that can actually enhance the rate of dephasing in the gravitational wave signal. Of course, the really key question is, what happens on merger? So you can ask a few interesting questions here. By the time we get to merger, is there any scalar field left, or has it all been dispersed? So here's an example simulation of this. So you can see that waves of the scalar field are being sort of thrown off as the merger happens, but you do have this kind of core of high energy density around the black holes before they merge. So it's entirely possible that this could have some impact on the merger signal. And that's something that we're investigating and is also being investigated by Helga Witek and her student Giuseppe. And I think it's the next sort of really interesting question to be answered. So this has been looked at, I think, for cases where you put a Gaussian of the scalar field around the binary. But a Gaussian is not a particularly well-motivated initial condition for the scalar field, because it wouldn't arise sort of over time. It really has to be put on by hand onto the binary. Okay, so I think I'll finish there. I just wanted to mention the outstanding challenges. So really at the moment, we are kind of looking at toy models. The real challenge in these models is to understand their robustness. And to do that, we really need to do very long timescale simulations. So I think these methods, so I mentioned Sam Dolan's method of decomposing into spherical harmonics, or using fixed backgrounds, so using some kind of hybrid numerical or analytic solutions are actually really important. We need to be a bit creative. We can't just throw a numerical simulation at everything. There is a point at which these are too expensive. One of the most interesting questions, I think, is what are the most well-motivated and appropriate initial conditions for merger simulations? So I mentioned that Gaussian, putting a blob of Gaussian scalar field around a binary is really not very well motivated. But there is a question around what is well motivated that still hasn't been answered. And of course, the really big question that hasn't even begun to be answered is what are the degeneracies with other environmental effects? So all of these effects are very small. The energy densities of these scalar fields, even in well-motivated cases, I gave you the example of superradiance, it's sort of a 10 to the minus 5 is the kind of number. So these are very small effects. So if we do want to detect them in something like LISA, we're really going to have to understand very well the degeneracies with other environmental effects or other parameters of the binary model. And that, that will require a significant amount of work that hasn't even begun yet. So I'll stop there and answer any questions if there are any. Thank you.